Welcome to our final webinar in the series entitled Introduction to Photonics Packaging. And again, I'm joined with my colleague Camilla Gratkowski, who today is going to be talking on the final topic of automation and design rules, and also provide some examples then of photonics packages that we have developed within the Photonics package group here in Tyndall. This webinar will last about 30 minutes, and again, we've left time at the end then for questions and answers, so please feel free to use the Q&A to input any questions that you might have. So I'll hand over straight away to Camille to begin the presentation.
Right. Hello, everybody. Thanks for joining us again. So after some feedback and some questions that I had accrued over the last 3 weeks, I decided to focus more on the automation design rule side and the example side. I hope you're going to find it interesting. So the first question is, of course, a very simple one, but why do we want to go for automation? People who are familiar with photonics packaging know that unlike electronics, which is largely very heavily automated, photonics packaging right now is in many parts all still done essentially by hand. And especially if you're dealing with things like prototypes, you'll know that photonics packaging is a very time-consuming process. This is due to the very high precision that we require to align the fibers to the chips, precision that can be of a single microns. And if we have to align several tens, sometimes even dozens of fibers to a single chip at the same time, it just takes time. An experienced person might require 3 hours. It might require less than 1 hour. It really depends on the package, but it is a time-consuming process. And as with all things, time-consuming, the cost of that is very high and volumes are very low. That's why photonics, especially the forefront of photonics, is very high value proposition, which is not very affordable on a larger scale. So, and also cost to market is quite prohibitive, which is why you see all those pilot lines springing up, and I'll speak about that later. And also innovation, if you come up with a new idea of a chip that you want to test, then going from the idea to a test, just a tabletop demo, that takes a lot of time and it costs a lot of money to do. Sometimes it can even take a year or even more. With some packages, we went through a 2-year development cycle just to showcase a new technology. So this is a very time-consuming process and very costly. And therefore, within packaging group, one of our major remits is that we want to move towards automation of all our packages at some stage, not perhaps at the very early prototyping stage, but we need automation. And of course, that is to drive down the cost of photonic packaging and make them very affordable. And manufacturing with photonics packaging, as you remember from my previous webinars, I was saying that we can take note of 5 decades of electronics packaging development and take many of the packaging techniques and import them directly to photonics packaging, use them in photonic packages. The only thing that stands out really is the attachment of the fibers, but we're working very hard on making that also quite scalable. And part of that process of scaling up is translation of the process. So on the right-hand side, you can see, I'll switch to laser pointer. So on the right-hand side, you can see more or less the schematic of the manual process at which that you package your chips with. So you put everything into machine. You grab your fiber arrays with your gripper. You put your pick onto the stage, and that's your preparation stage. Then you correct the angles between your fiber array and your pick to make sure that they're aligned very well. Very critical step, you have to find the first light, otherwise you will not have anything to optimize, after which you run through several renditions of position optimization and any final angle correction, upon which, after you found your optimal position, then you use typically an optical adhesive to attach your fiber array to the chip. And so this is how it looks like from the manual standpoint in a broad sense. But you need to translate that process into an automated into an automated one. And on the left hand, this is like a block diagram of an automated process, and if you trace these steps, these can broadly be put into categories within this process. So some steps require several iterations and so on, but the translation from one to the other is a critical step, and you need to be familiar typically with the manual step before you can go to automation, because you need to know what happens during each manual step in order to properly translate it. And automated packaging machines are very similar, just the manual machines. Here is an example of a machine we have in our lab from Photonic. And if you compare it to a manual machine from any company, that they look very similar. Ours has 2 alignment arms and at least 3 cameras. Originally we had 4. One was removed for space reasons, and there's also a package holder here in the middle that holds the chip that needs to be packaged. And each of the alignment arms has a 6-axis stage, of course, because we need not only position but also angular alignment. There's a set of grippers to hold the fiber array. There's an epoxy dispenser as well for automated epoxy deposition. But critically, there is a stage camera. And this allows for determining the orientation of the grippers in space, because there's direct registry between what the camera sees and the position of the camera and the position of the grippers. It can be hard coded into the software. However, you can see that this camera is indispensable in actually getting the bearing, so that the machine knows the position of the package relative to the position of the grippers. And if the machine can't see it, you won't be able to perform any sort of these advanced automated packaging steps. Alignment markers are also quite critical for the packaging process. They're positioned typically on the chip, and they have to have several key features. So they have to be sufficient size so that you can actually see them with a camera. If they're too small for the effective pixel size to see, then you won't be able to register them properly. They have to have high contrast. They have to stand out from the background. Typically, it's done very easily by just putting a metal layer on the chip that gives you high enough reflection and contrast. They have to be characteristic. That means distinguishable from anything else from the chip. Otherwise, the machine can be confused at actually what set of alignment markers does it see. And it also has to be the machine has to be able to filter it against the background noise. And the distance between the markers essentially determines the accuracy of the measurement of the position on the rotation of your chip. And you need at least 3 of those to establish the orientation of the pick relative to the machine. If you have just 2, your accuracy is not that great. And as for the shape, they can be essentially anything, but most typically you'll find squares, crosses, circles, or combinations of. They can be positive to negative. It really doesn't matter that much. So here's an example of actually there will be a series of videos on which I will be showing the examples of actually how the machine in our lab recognizes the photonic circuit position and orientation, and how it aligns the fiber array to it. So let me run this out. So you can see a reference chip on which we figure out the X, Y, and Z position as well as orientation of the chip using these sets of squares, which are registered against the couplers, the edge couplers, which are on this chip. So we look for sets of them in each of the corners, and once we find them all, we can actually calculate the position of each of the edge couplers, which are present on the chip, as well as determine the orientation of the photonic integrated circuit relative to the angle of the fiber array. And this is done in a series of steps similar to before. First, as you can see over here, the machine is determining the orientation of the fiber array using the corners of it. First, there's a camera which is outside of the field of view on the right and looks from the bottom. This is to show the orientation in this is the yaw angle. And then the angle shifts to looking from the side to determine the pitch of the fiber array relative to the chip. Then you also can find the yaw of the chip, but afterwards, after all the angles are corrected, since the machine knows the position of the edge couplers relative to the position of the grippers, now it can very safely approach the chip with the fiber array and continue the process from there. Here is a little bit more advanced machine, again, by Tech, on which you can see a process which is a little bit different, but still shows some features of automated packaging process. In this case, where this is purely electronic-based process, in which we pick up the glass interposer and move it onto a soldering station. You can see here there's a lens from the bottom through which the laser is going to actually be shown onto the chip. So first, the bond pad positions, after putting them on the reflow stage, are identified so that machine knows their orientation and position in space. Then you pick up your silicon part to be soldered using the same pickup tool of which you picked up your glass interposer. It's just done very gently using vacuum. Then it's deposited onto like a holder stage so that the real tool can be brought into. So this tool actually has a window through which the laser is going to be shown. This is a very special tool that uses combination of vacuum. It's essentially a vacuum pickup tool. Again, the machine picks up some orientation markers. In this case, it looks for specific bond pads in order to orient them properly with the substrate below. Then, of course, it measures the pitch and roll of this piece in order to match it to the interposer. And then once both parts are brought together for bonding, the laser is shown through for a few seconds, and the temperature reaches the reflow conditions in just very quickly. So it was a second or two, and afterwards the part is released. So this is an example, let's say, of a more electronic-based automated packaging process. And afterwards, the package can move on to a let's say for fiber alignment and attachment. So you can see the automation in this case looks more advanced because this is like the microelectronics based process, which is takes from the legacy that we've built upon for several decades. And then you take this part and you put it in a different machine for an automated fiber attachment, for example. So you cannot perform you cannot start thinking about any sort of automation until your package conforms to some sort of standards. And we call those typically design rules. So here's an example of a package which we encountered very early, like about perhaps 10 years ago, that whereabouts, which required very specific conditions to be packaged. So you can see there's a lot of things wrong with this photonic integrated circuit. One stark feature is that it's kind of rotated, and that's because the waveguide leaves at an angle here. So in order to conform with the package definition, we had to actually approach it with a lensed fiber that was coming normal to the package. So we had to rotate the PIC itself to conform to that angle. So that's one thing. Second thing, the bond pads for electrical integration are essentially all over the place. Typically, what you'll find now is that they're positioned at the edges for easy wire bonding or other sorts of integration. In this case, it was we had to move even some of the bond pads through some very warehouse, like a very the interposers were essentially made in-house. And in this case, if we try to take this package and put it in through the automated process, that would be impossible. And even if possible, it would require a very specific machine. Machine would be built exactly just for this process. So what we advocate here is to conform to standard design rules so that your device, even if it's an early stage of development, can conform to those rules, and therefore it can be moved through the scaling up pipeline much faster. And those design rules are quite simple. Here's an extract from the book. There's several design rules, and each packaging house or each pilot line will have their own set of design rules, but they're generally quite similar. For example, you shouldn't put your optical and electric connections in such a configuration that they can interfere with one another. For example, having your fiber connections very close to the electric connections to interfere with bond pads, for example, or having north and west for optical connections and your other parts for your electrical connections. This is typically not very good design. Also intermixing them, as you can see here, so that all your optical and electrical connections are on one side of the chip. Typically, what we advocate for is a clear separation of domains. One direction is for optical channels. The other direction is for electrical channels with additional separation between DC and RF. This is, of course, not always possible. Sometimes you have to mix your bond pads, DC and RF, but such a configuration gives a very clear it's a very clear method that leads towards standardization and ease of packaging. And then once those design rules are essentially built, they can be, the reason why they're so important is that they can be incorporated into other piece of software which are used by chip designers for designing chips. So once they're incorporated into software such as, what's the software? I'm not entirely familiar with the software name, but once you use the software to design your PIC, then you can run a check against the packaging design rules, and it can tell you that, for example, your bond pads are too close, or they're not positioned correctly relative to other parts of the chip. They're for example, too close to the edge, too far from the edge, or they're kind of intermixed. So the packaging design check it can be an invaluable tool for PIC designers as well. And the way those design rules are defined are using something called reference chips. So each reference chip essentially is a simplified version of a photonic integrated circuit in that it contains only the relevant interfaces. So it doesn't contain really any active parts in the sense that that its purpose is not to be a working device. Its purpose is to be a packaging test vehicle. So they would contain things like couplers, waveguides, DC and RF bond pads, heaters, everything necessary just to test out your packaging techniques. And this is one of the examples on which you can see that we have here a series of edge couplers, rows of grating couplers, DC and RF bond pads separated north and south. We have some placements for electrical flip chip testing, as well as heaters for thermal management testing. And this allows for development not only of your packaging process, but also for development of packaging equipment. And the reference PICs have this advantage that they're quite simple to make. They can be much more simple to make, and you can get them from a single wafer by tens, dozens, or even the hundreds. So there could be quite an easy way to test some of the packaging techniques that will be relevant for the device, for the system. And you can even combine different types of your reference chips to get what's called reference devices, which you can use to simulate the entire systems as a whole, how they behave electrical wise, optical wise, and RF wise, as well as thermal wise. So here is just a very quick sketch of which you can see we're combining a reference PIC, which is the optical part, an RF PIC, which would simulate, for example, your controller, and thermal EIC, which would be like a simulation of the thermal aspect. So how much heat is generated within the enclosure of the device. And combining those reference chips together, you can actually simulate the packaging process as well as the general behavior of your device packaging-wise. So this is quite critical for developing of packaging techniques. And then from those, you can actually develop those specific single packaging techniques. So you can create a menu of that you can offer to to your client. So for example, flip chip of a single die is one packaging technique that you develop using those reference picks. Then you can move from a single die to wafer level integration. For a more control of a package, you can actually show how your package behaves, when a specific thermal load is applied to it. Flip chipping, high speed pick and place is another technique that's essentially a legacy of microelectronics. You can showcase, how you deal with wire bonding from both DC and RF aspect. Then you can also introduce other items to your menu, for example, interposer integration. For example, this is a quite sophisticated package which contains a fiber array going for a triplex chip interposer into the indium phosphide chip. You can also add to the menu lenses, which are written directly onto lasers for integration onto the waveguides. You can write lenses onto your waveguides. Onto waveguides to couple to fibers, and other standard packaging process. For example, of course, integrate attachment of fiber array to the chip from both the edge and grating copper side. And once you do that, you can essentially combine them into what's called the technology demonstrators. So these combine all the technology and techniques and elements that can be found in majority of packages in the most generic terms. So for example, here we have a TX transceiver, which has hybrid laser integration, electronic integration, micro-optic integration, DC and RF wire bonding. And this is just a vehicle to demonstrate the technology, even though this is actually a working device. And yeah, this is just a listing of all the techniques that are used for demonstration of this specific technology. While the chip itself is a working device, this is actually a device to highlight the capabilities of packaging, what can be done using packaging techniques as they currently are. Europractice, of course, also has a set of standardized integration services that you can take advantage of. So you can take advantage of advanced photonic packaging. You can have fan-out wafer level packaging using interposers. You can have pre-packaging wafer level services and even microfluidic system integration. And for the full list, you could go to the site to see what sort of services can you avail from Europractice. And we also have in Europractice some standardized packages that as long as your pick, which is the center over here, sorry, my mouse keeps moving, as long as it is designed to the standard that's defined from Europractice design rules, you can get a very easy way to package your device, because we have standardized PCBs, heat spreaders, stacks, bases, and as long as the pick is well designed to conform to these, this is a very easy way to have your chip packaged at a relatively low cost, and you can do that for both grating and edge coupling designs. However, the future of packaging is a little bit different. The way that we see it, because all the processes that you see that I highlighted here, even automated, especially as part of the photonics integration, so attachment of fiber arrays, those are serial processes. They're basically done package by package, which means that even automation can only give us there's a limit at how much scaling up to volume can that give us. In the serial process, this is the limit is quite low. So in the future, what we're looking towards is making packaging process not serial, but parallel. So the basic idea here is to use the chiplet model that's becoming very popular, on which you have essentially an electrical and thermal interposer, essentially a wafer of interposers. So you can see each tile is its own interposer, and on each of those you integrate all your electrical and optical components, so your EICs, your PICs, and all the components necessary for a working device. And once that is done, once the assembly process is done in a parallel manner, then you can optically test it and electrically test it on the same wafer before you dice out your device. So this is a very easy way to parallelize the packaging process and scale it up to actually quite high volumes. And what you can think about is also that we can use the what's called the multi-project packaging runs, where each, perhaps not each, but there can be several series of tiles which have different designs from different customers, or or different iterations, so that you can just pay just for your part and have just a part of the wafer packaged. And this is the way that we see to actually scale up to very high volumes, which would be quite necessary if when the AI becomes even more when the photonic devices become much more ubiquitous in applications such as AI, which is a current very high visibility requirement. And as I mentioned, yes, you can. This can only be done if everything here is standardized. So all the, not only the parts but also processes are standardized. Only then we can move on through these steps from just a single, package by package process to automated process, and then scalable parallel photonic device assembly. Are we on time? Perfect. So takeaway message from this part is essentially that, of course, we need automation. That's essentially, that's the only way that we can make it affordable, not only for for the big players but also for SMEs. And in order to get there, you need to know how it is done from the manual perspective, because you need to then be able to translate it to an automated process. And for automation to be possible, you need to follow a set of design rules which are codified in what we call assembly design kits, or ADKs, which is essentially the design rule package for packaging. And the packaging processes and the equipment then can be developed to follow those design rules using quite cheap reference picks. And once that is done, then you can move on to more device-centered approach, where you combine several of your reference device picks to have reference devices and showcase your packaging technologies that you can provide. And finally, the technology demonstrators are the final vehicles for showcasing the capability and compatibility with volume manufacturing. So that was it for automation design rules. Now, several examples from our own, from our own in-house development that showcase some of the aspects of photonic packaging. I will be showing exactly how the sausage is made, but hopefully this gives you some idea of what photonic packaging entails. I've chosen two examples. One is a 4-channel transceiver, actually the same one that I showed briefly later. So this is a transceiver which has 4 channels for transmission and 4 channels for receiving. It's operating at 50 gigabits in on-off keying per channel, and the wavelength is 1310 nanometers. So the design of the PIC is, of course, very important. We have our, let's say, our control layer over here, which will be composed of several electronic integrated circuits. Then there's the modulator section and the coupling section. In this case, we take this source of laser, because this is a silicon-based PIC. We take a source of the laser light from the outside. I'll show how this is integrated a little bit later, through this grating coupler over here on the surface. And it travels, and then it's split into 4 channels. Each channel is individually modulated and is output through the coupling array, again, based on grating couplers. The returning light from the system is coupled to a row of 4 detectors. You can see here one feature that's critical for packaging. You can see this shunt or loopback. This is necessary for packaging of the coupling array. And this is typically necessary whether you have your micro lens or you have your grating or edge coupler. You need some sort of a shunt or loopback in order to align them properly. So this is the optical layer of this device. The electrical layer of the PIC contains the amplifier IC to amplify signal from the detectors, and modulator integrated circuit to modulate the signal of the modulators, and they are serviced by a set of RF connections you can see here from the side, as well as a series of DC connections just to provide power to the entire device. So these are separated, of course, but since they're in quite close proximity, we couldn't separate the RF and DC channels completely. They had to be a little bit mixed. However, there is a clear demarcation between the electrical part and optical part. So this is the complete design of the package. In this case, we used a pluggable outcoupler based on the MPO or MTP system, and the entire package is composed, it essentially is servicing the electrical side. There's a row of, well, it's difficult to call the row, it's like a ring of RF connectors and a row of DC connectors for powering. This package is assembled in several steps. First, the electrical layer is being serviced by depositing solder balls onto the bond pads over here, upon which you flip chip bond your EICs onto both series of pads. Then you integrate a micro-optic element just by gluing it onto the surface of the PIC. And finally, the last step is to integrate a laser. This laser is actually based on micro-optical bench system where you have a laser chip sitting on a ceramic surface. There's a ball lens in front of it and a turning mirror prism, which turns the light to satisfy the angle of insertion. I think in this case it was 10 degrees. So this laser is integrated in such a way that it couples light into this grating copper on the surface. And the entire PIC, once it's assembled on its own, then it's integrated into the larger system. We place it on the heat spreader and wire bond it across. We use ribbon bonding for RF connections and standard wire bonds for DC connections. And this is let's say the overview of the finished package centered on the PIC, where you can see all the wire bonds and all the connections being being made. Finally, the optical layer is being assembled. So the MPO connector is assembled into the socket, and in this case it's actively aligned to the chip. I think there's a video on the next page, which means yes. Sorry. Yes. So this is just an example of the operation. Here you can see the eye diagrams on the right. And since this is a pluggable connector, by using micro-optics, you can see that plug-in and plug-in MPO connector actually returns the signal to the level that it was. So that was, let's say, our more data center based demonstrator that we did. Another one is a little bit more centered on medical applications, because photonics is not only, although primarily is being used for data centers and telecom applications, but things like LiDAR and critically medical applications are a huge part of photonics nowadays. So in the group, we had several projects which demonstrated some medical applications of photonics, as one of them was a European project called CARDES, which used laser light to measure the velocity of the pulse in a patient's neck. Essentially, it used the vibration of the skin in order to determine how fast the pulse traveled through the carotid artery on the side. I don't remember which side of the neck. I think it's this one, on the right side of the neck. And from the shape of that pulse and speed of that pulse, you can determine early signs of cardiac issues. That's before this project, it was typically done using, I believe you had to apply some electrical leads in various parts of the body, and you measured essentially electrocardiogram. But with this, you can do it using optical means. So design the PIC essentially centers around sending light out from the photonic integrated circuit out into space. And this is done using a series of antennae. So these antennae are essentially grating couplers, which one is for coupling light out of the PIC, and the other is to collecting returning light. So there's a series of them. I believe there's 6 of them in the row, and they're serviced by a single hybridly integrated laser, again, based on the micro-optical bench idea. In this case, the micro-optical bench has also integrated isolator to keep any feedback going back to the laser, which could affect the measurement. Optical design, of course, was quite critical because we are coupling light into free space from a single chip using a series of lenses. So one lens is the big lens that focuses onto the patient's skin, and the one lens that essentially collimates, pseudo-collimates the light out of the PIC and collects the returning light back. You can see here there are several spot aberrations from the simulation, but that in the end turned not to be a big issue. So electronic design was not very complicated. Essentially, it was a PCB with a series of photodetector amplifiers to detect the returning signal, because of course you might imagine that the reflection and the collection efficiency of light returning back from the patient's skin is quite low, so the signal had to be heavily amplified. Since this was this was supposed to be a handheld device, not like a big machine, but a handheld device. So everything has to be quite compact, and this kind of shows the design. This design philosophy is shown in all stages. So, for example, you can see here everything is done with a flexible connectors to save as much space and volume as possible. The same is done also for thermal design, where all the thermal management has to be quite compact. And in this case, it was actually quite simple. This was just a thermoelectric cooler and a large aluminum radiator just around this area to manage the package. The entire design is shown here. We have our electronics bay in the back. We have, let's say, the thermal management stage and the PIC in the middle. The PIC is, of course, tilted at an angle so that the light escapes from it parallel to the axis of the device. And there are 2 outcoupling lenses, as well as some visible aiming lasers to help, to position the device. And you can also see that this device is it's essentially a pistol grip design to be handled by a surgeon in a very ergonomic way. I won't go through the optical assembly part because this just shows like snapshots of various processes that are required for for aligning the package optically. So you have to align the large lens, then you have to align the ball lens very precisely to the PIC itself. And finally, you have to also align the targeting beams so that they're focused on the same plane, so that they're very well registered against your infrared signal, because the beam was infrared. And here you can see the final package. It's actually composed of 2 devices brought in together. This was tested actually at a hospital in France. Here you can see a short video that was shot by a television station. You can see here the arming lasers coming together onto the patient's skin, and using these 2 devices, you can measure the vibration of the skin as well as the pulse, how it travels through the cardiac artery. So again, the takeaway message perhaps for the whole series is that yes, photonics is very important, and packaging is a critical aspect of the photonics that enables all the cool devices that we see in the market, and the ones that we haven't yet seen. So in order to make these technologies ubiquitous, you need a packaging-oriented design. Even when you're designing your chip, you need to think already about how it's going to be assembled in the final device. Otherwise, it might take much longer from getting from the idea to the actual product that you can sell. So thank you again for listening to not only to today, but to the entire series. And if you have any questions, we have time.